So here is fundamental theorem of calculus, right? So it says, first, it needs to be continuous on the interval AB. If it is, we create another function where g at x is the area under the curve from A, let's say this is f at t, okay, this is t, and the variable, the input, right? The input goes on top of the integral. Meaning, it's a function which gives you the area under the curve by varying the location of x. That's what this function is. You have to understand that. Okay, so meaning that this function is fixed, it won't change. What we are varying is this x. Then, the derivative of this g at x is f at x, meaning the derivative is equal to the function itself, f. So yeah, let's prove that, right? So you know the techniques in integral calculus and differential calculus exist for that, like probably 1,000 years. Right? People have been using it to construct fancy buildings, round structures, and so on. Right? But the connection, making the connection of integral is somehow related to the derivative and back and forth, was connected by Newton. Okay, so Newton's, a lot of people think Newton created calculus. He didn't create calculus. He just unified it in a way. he made it to make all sense. Okay, so let's do the proof. So we're trying to show that if this is g at x, the derivative is f at x, right? Okay. So g prime at x, we know that by definition is this. Right? Okay, so let's figure out what that is first. So g at x plus h minus g at x is the following. Integrate from a to x plus h. And a to x for f at t dt. Right, so do you guys follow so far? All I did was use the definition of g, right? And wrote it like that. Now using the property of integrals, I can change that into a to x f at t dt, x to x plus h f at t dt. And leave the back part alone. Not do anything with that yet. And when I do that, look. So really, it's just the integration from a to x plus h. Sorry, a x to x plus h f at t dt. Okay, look. So we have x. And we have h is a really, really small number. Okay. And we have a function f that passes through there. Now remember the comparison property of integrals. At every continued function, right? At its interval, the interval of x and x plus h, there's going to be a minimum value of m, and there's going to be a maximum value of big M. Right. So the comparison theorem says this. This here is in between m times the interval, which is h, and big M times the interval length, which is h. Okay, so that's what I'm using. We talked about this last class. Okay, so Now I'm going to divide the center by h. But if I want to do that, I have to divide everything by h. Because what we originally wanted was this differential quotient, right? What I have here is just this top part. So I divide by h to get the derivative expression. So 1 over h integral and we get this. Okay. Now look, let's let where it's m, let's call this u. Okay. In this picture, where the m occurred was x, but it doesn't have to be like that, right? It could be something like like this. And then this would be the lowest. Let's call that u. Let's call this highest point v. So that will be the big M will be f of v, and let's call this one the small m f at u. Okay. So I'm going to replace that with f at u. And f of v. Okay, follow so far? Now, if I just attach a limit to the center, this right here is the derivative at g, the derivative of g, sorry, the function g. Now what happens is h approaches to 0 for u and v. As h approaches 0, right, this interval is going to get really, really skinny. Right? So both u and v, which is squished between x and x plus h, is going to approach x. So these guys are essentially, right, going to be this. I just proved it. Right? So the center expression is g prime at x. I just showed you guys that this will be essentially, by squeeze theorem, this. Okay, so that's the fundamental theorem of calculus. So let's do some application. Now, the really important thing is this. Okay, that's okay. If you differentiate, you get f at x. So then, if I have a function, I want to know its integration, right? What you have to do is find the antiderivative. Right? Do the derivative backwards, and you get the integral. Right? That's what it's implying. Right? If you differentiate, you get the function. So if I want to go back to here, if I want to know what g at x is, which is the integral, I gotta find the antiderivative of f at x. Okay, so we'll talk about that more.